Most machines are built with safety margins, alternative designs, and tolerance for failure. These Russian machines are different. They are designed to operate where margins disappear. Rescue is uncertain, and failure is expected. This is engineering pushed to its practical limits. Nuclear icebreaker class. These vessels are the most powerful icebreakers ever built, using nuclear reactors that produce over 60 megawatts of power, comparable to a small power station dedicated entirely to propulsion. Instead of cutting through ice, they ride up onto it and crush it with their own weight. This creates continuous structural stress rather than short impacts. To withstand this, the hull is made of reinforced steel, and the bow shape is designed for repeated loading cycles. They can move through ice more than 3 meters thick and operate for months without refueling. Reactor refueling intervals are measured in years, not weeks, eliminating one of the greatest logistical risks of Arctic operations. Their importance lies not in speed, but in long-term reliability under continuous mechanical stress. Over-the-horizon radar. During the Cold War, this system was built to detect ballistic missile launches at extreme distances, using high-frequency radio waves reflected off the ionosphere rather than direct line of sight. This required transmission power levels strong enough to cause interference across vast areas of the planet. Engineers in many countries recorded the interference years before the system's purpose was officially acknowledged. The antenna arrays stretched hundreds of meters and required precise synchronization of thousands of elements. Small atmospheric variations could affect detection accuracy, requiring constant recalibration. It is notable for operating in a region where radio wave behavior becomes unpredictable, trading precision for early warning. Poseidon Status 6 Underwater Vehicle. This system was designed to operate at extreme depths and long distances, where communication with human operators becomes impossible. Its existence has been officially acknowledged, though many technical details remain classified. Open sources estimate that it is nuclear-powered, allowing long-duration operation without refueling. Its navigation is believed to rely on inertial systems combined with seabed reference methods to limit long-term drift. Designing autonomy at such depths presents challenges related to pressure, heat dissipation, and long-term system reliability. From an engineering perspective, its significance lies in sustained autonomous operation where recovery or intervention is not possible. Bell AZ 75710 mining truck. This vehicle was developed for very large open-pit mines, where reducing haul cycles directly lowers fuel consumption, labor hours, and overall operating costs. In such environments, scale becomes more efficient than speed. Fully loaded, it weighs nearly 1 million kilograms, making it the heaviest land-based work vehicle ever built. To prevent ground collapse, engineers distributed this mass across 8 tires, each over 4 meters tall, designed to operate under extreme pressure without overheating or structural failure. Power comes from 2 diesel engines, each producing around 2,300 horsepower, driving generators that in turn power electric motors mounted in the wheels. This diesel-electric system eliminates traditional gearboxes, reduces mechanical stress, and allows precise torque control on uneven mine surfaces and steep grades. The truck uses dynamic braking systems to safely absorb enormous kinetic energy during downhill runs, critical for deep open-pit mines. Even the braking systems are designed for continuous stress rather than short loads. The Bell AZ 75710 is not experimental or symbolic. It operates daily in active mines, often around the clock. It represents the point at which conventional vehicle design no longer scales efficiently and only extreme size remains practical. Arctic offshore oil platform. This offshore structure was specifically designed for Arctic conditions, where drifting sea ice applies continuous horizontal pressure rather than short-wave impacts typical of tempered platforms. It uses a gravity-based reinforced concrete foundation weighing hundreds of thousands of tons, resting directly on the seabed. Instead of rigidly resisting ice, the structure is designed to absorb and distribute ice loads, reducing the risk of brittle fracture at low temperatures. Oil production, processing, and storage are integrated into the same structure, with storage tanks built into the base. This allows oil to be stored on site and transported during limited ice-free periods, reducing reliance on annual shipping through frozen waters. Because evacuation may be delayed for weeks during winter storms or heavy ice, the platform is designed for long-term autonomous operation. Critical systems are redundant, spare parts are stored on site, and maintenance programs are designed to be carried out without external support. The platform represents an engineering approach focused on endurance rather than mobility, accepting isolation and constant environmental pressure as permanent operating conditions rather than exceptions. EKG-10 electric mining excavator. This excavator has remained in use for decades because it was designed around mechanical simplicity rather than maximum performance. Instead of pursuing higher speeds or lighter components, engineers prioritized durability, ease of repair, and predictable behavior under continuous load. Using electric motors instead of internal combustion engines eliminates several major failure points, such as fuel injection systems, complex gearboxes, and high-frequency vibrations. Electric drives provide consistent torque at low speeds, ideal for continuous excavation and reducing stress on structural components. Key parts are deliberately oversized, operating far below their maximum limits. Combined with slow, controlled movement, this keeps temperatures low, minimizes metal fatigue, and allows components to last far longer than modern high-performance machines designed for short duty cycles. The excavator can move large volumes of material for hours without frequent shutdowns, making reliability more important than speed in large mines. This approach reduces downtime and simplifies maintenance planning. Overall, the machine demonstrates how reducing complexity and operating below maximum capacity can dramatically extend service life in harsh industrial environments, even at the cost of performance or modern features. Industrial environments, even at the cost of performance or modern features. Vityaz DT-30 articulated tracked vehicle. This vehicle was designed to operate on snow, tundra, swamps, and ice, where wheeled vehicles cannot function. Each section is amphibious, allowing it to float on water and broken ice. Its wide track system distributes weight over a large surface area, reducing ground pressure. It can operate at temperatures below -50 degrees Celsius and is used to transport fuel, equipment, and personnel in regions without permanent roads. Its value lies in maintaining mobility where no infrastructure exists. MAZ-7907 Heavy Transport Vehicle. This machine was built to transport loads so heavy that conventional trucks and trailers could not move them safely. The challenge was not engine power, but how to move such weight without destroying the ground or losing control. Engineers solved this by using 24-driven wheels, distributing the load over a very large surface area. This reduced ground pressure and prevented sinking into soft terrain. An electric transmission system allowed precise torque control at each wheel, which was critical for slow movement under heavy load and for minimizing wheel slip. Mechanically, the vehicle performed as designed. The real limitation was infrastructure. Most roads, bridges, and turning areas were never built to support a vehicle of this size and weight. Route planning became more difficult than operating the machine itself. This vehicle shows how engineering can solve a technical problem while simultaneously exposing weaknesses in surrounding systems that were never designed to accommodate such extremes. Mency Muck Walking Excavator. This machine was developed for steep and unstable terrain where conventional track machines cannot operate safely. Independently adjustable legs allow continuous repositioning to maintain balance on slopes, riverbanks, and cliffs. Operators actively manage stability during excavation. Its design allows work in areas that would otherwise require extensive ground preparation or would be inaccessible. Its usefulness is defined by adaptability rather than power. Rail Mobile Missile System. The missile was hidden inside rail cars disguised as ordinary refrigerated freight wagons. These trains move through the national rail network alongside normal civilian traffic, stopping, changing routes, and blending in with thousands of other trains. From satellite imagery alone, they were extremely difficult to distinguish from standard freight trains. The launch equipment was integrated directly into the rail system, allowing missile launches from regular sections of track without special launch sites, further reducing predictability. However, this created serious mechanical challenges. The system had to remain fully operational despite constant vibration, temperature changes, and mechanical stress from continuous movement. The design demonstrates how transportation networks can become part of a defensive system, using movement and uncertainty instead of fortification to make detection and targeting far more difficult. These machines are often described as extreme because they operate close to the practical limits of engineering for extended periods. Their designs reflect deliberate trade-offs between efficiency, durability, redundancy, and survivability. Rather than defying physical laws, they reveal how much safety margin is usually built into conventional systems, and how much that margin can be reduced when conditions demand it. Studying these machines offers insight into how engineering adapts under the pressures of geography, climate, and strategic requirements. Their significance lies not in spectacle, but in how they extend the boundaries of what is considered operationally possible.